Hello, everyone. We will just take just 1 minute to let everyone into the room and then we'll get started. Well, good morning. We will get started. We are going to have a great presentation today from Ed Lohrenz from GEOptimize and John Fabre of Otter Power. And they'll be giving a joint presentation, giving us a deeper look into commercial design. So this presentation will include a description of the Otter Power Geo Incentive and Design Assistance Program. And then the second part will go over the benefits of iterative hourly energy modeling compared to using rules of thumb to estimate the feasibility of a geosystem. And then we'll go through some case studies. So we welcome any questions that anyone has during the presentation, but if you could just please include those in the chat function, that would be wonderful. And we will read those at the end of this presentation. So without further ado, Ed, John, if you want to take it over, that'd be great.
Thanks, Courtney. John, do you want to start first?
Yes, I sure can, Ed. Thank you, Courtney. What I'll cover today is just some background on Otter Power Company. We're a smaller investor-owned utility operating out of Fergus Falls, Minnesota. So not a real big name. So I thought a little bit of background on what we do and how we go about doing things would help. And then I'm going to talk a little bit more in detail on our energy efficiency programs in terms of the results that we've seen, specifically the programs we offer, and then finally some detail on what we call the Integrated Building Design Plus program. And that's the one where we really team up with Ed and the folks at GEOptimize on bringing these geothermal services to our customers. So just to start then, our vision at Otter is growth and success for our company and the rural communities we serve. Hang on just a second, I have to close this window down so I can see my screen. Sorry about that. We collaborate and prosper through responsible, resourceful action. We balance community, economic, and environmental commitments always. Our mission at Otter is to produce and deliver electricity as reliably, economically, and environmentally responsible and environmentally responsibly as possible to the balanced benefit of our customers, shareholders, and employees. And the key word there is balanced. We'll see that a little bit in future slides. And then to improve the quality of life in areas in which we do business. We make decisions on our 5 core. Ed, could you back up, please? Yeah, we make our decisions based on 5 core values of integrity, safety, customer focus, resourcefulness, and community. Thanks, Ed. This slide just illustrates graphically where we operate at Otter and a little bit on how we generate electricity and where those generation assets are located. You can see we serve a pretty rural customer base just by looking at this map. We operate out of Fergus Falls. And we provide service for customers throughout North Dakota, Minnesota, and South Dakota. Our generation assets include some wind resources located throughout North Dakota, a coal station that we own jointly with other entities, but we operate exclusively near Garrison, North Dakota, another coal plant located in Big Stone, South Dakota, and another coal plant in Fergus Falls. However, that is just recently started undergoing decommissioning. We feel that this service territory makes us pretty unique, and this slide just provides a few more details on the rural and small community nature of our territory. In Minnesota, 90% of the communities we serve have got a population of 1,000 or under, and only 1.5% of the communities on average have populations exceeding 10,000. That's a little more extreme in North Dakota, with 93% of our communities we serve with having populations under 1,000, and only 0.2% of those communities with populations exceeding 10,000. And in South Dakota, 91% of our communities at less than 1,000, and no communities in South Dakota that we serve with populations exceeding 5,000 people. And for us at Otter in generating electricity, it's all again about that word balance. We feel our mix is diverse, it's low cost, it's reliable, but it is increasingly clean. It ensures affordable electricity 24/7, and it's constantly evolving with innovation. Our 27 to 2031 resource plan targets more than 30% of our electricity coming from renewables by 2021. And we've made a commitment here to balance. We're proud to live our commitment in part through the mix of the energy resources we provide. This slide just shows graphically how that mix has evolved over time. In 2001, we were relying on 80% of our electric generation from coal resources and just 10% from renewables. Move out to 2021, and that's shifted to just a little over half. We've decreased significantly in what we provide from coal, and renewables have increased to nearly 1/3. We really, at Otter Tail, we rely on two key areas to set ourselves apart from a competitive standpoint. Those are prices and customer service. You can see our residential average rate is about just under 10 cents, about 9.5 cents. That compares nationally to about 13 cents. So we're about 30% lower than the national average in terms of our average residential rates, and that is reflected across the 3 states we serve. In Minnesota, we're about 2.5 cents less than the state average. In North Dakota, we're about a penny under the national average, and in South Dakota, again, just a little over 2 cents under the state average. Customer service is that other area that we rely on to really stand out competitively. And we use the J.D. Power residential customer satisfaction study to a pretty great extent here at Otter Tail. And we rank 3rd in the Midwest midsize region. We strive to rank in the top 3 usually. The study measures customer sat with electric utilities by examining 6 different factors. Those include power quality and reliability, price, billing and payment, corporate citizenship, communications, and customer service. So we strive to stand out in those areas. In terms of energy efficiency programs, we bring these programs to market under a number of regulatory and statutory requirements. The first being a 1.5% energy savings goal. That changed in about 2010 from a spending requirement, where we just had to take an average of our annual gross revenue at Otter Tail and multiply that by 1 or 1.5%, and that's what we had to spend. In 2010, the Next Generation Energy Act shifted that to a savings-based goal with specifically 1.5% energy savings goal. So every 3 years, we file a detailed plan with the state with a budget laying out specifically how we're going to meet these efficiency requirements, what programs we'll use, and how much we'll spend. In 2020, we actually met 4% energy savings with just over 70 million kilowatt hours of savings. Our statutory spending requirement, even though it's savings based now, we still have a minimum spending requirement. That number in 2020 was just over 2.3 million. We exceeded that by quite a bit with 9.6 million in spending. And another requirement we operate under is that a certain percentage of our spending has to be on low income programs. That worked out to about $150,000 in 2020. We exceeded that number by 44,000. And then finally, we have a statutory requirement that states that we have to include 1 or more programs in our portfolio that supports Energy Star for buildings, LEED, or Green Globes. This slide just illustrates a little bit the results that we achieved in 2020, specifically where the savings came from. About 68% of our kilowatt hour savings were attributable to the commercial and industrial sector, just over 1/4 to the residential sector, 5% from something we call program development and regulatory programs. That's basically a small solar program, and we're allowed to spend a certain amount of money on that program. I think that slide showed the spending was right in line as well with the savings, a little bit different, but very similar. We achieved these results through a number of different programs, both residentially and commercially. On the residential side, we have a home energy management program that consists primarily of load control for air conditioners and water heaters, an appliance program that provides rebates for the purchase of Energy Star appliances, as well as an incentive for customers to recycle old, inefficient appliances, a home lighting program, an energy feedback program that's kind of unique in that it sends reports out to customers showing how they use energy as compared to what we call neighbors or owners of similar size homes throughout our territory. We've got a home heating and cooling program, which encompasses rebates for both geothermal and air source heat pumps, smart thermostats, and then home envelope upgrades. And finally, a home direct install program that consists primarily of energy efficiency kits that are sent home with students, as well as a lesson plan incorporated into those 5th and 6th grade lesson plans at the schools. On the commercial and industrial side, very similar to many other utilities, we have some prescriptive programs they provide cash incentives for installations of adjustable speed drives and premium efficiency motors, various compressed air efficiency equipment, heat pumps, both geothermal and air source heat pumps, lighting retrofits and new construction, and efficient refrigeration systems, along with a number of other programs like a direct install program that focuses on free installation of low and or very low cost measures in small to mid-sized businesses, an audits and studies program that includes compressed air audits. It includes as well as building recommissioning studies. And then finally, our integrated building design plus program, and I'll go into a little bit more detail on that now. The integrated building design plus program, or we call it the IBD plus program, is an opportunity for architects, engineers, and energy experts to team up early with their client and our customers in the design process to coordinate and optimize all building design components and systems. The goals of the process include designing a building with operational costs as low as possible, a building with as little environmental impact as possible, and a building that will maximize worker productivity. And then we aim to incorporate all these features with minimal increases in first costs through this process. The customer benefits to participating include, first of all, no-cost energy modeling of proposed design packages. Through this modeling process, we show them a few different bundles of efficiency upgrades and projected extra costs, and then the savings from those upgrades into the future. We provide compensation for the design team members on the customer's design team to participate. There's often some extra time through the modeling and participating in a series of meetings, so we want to compensate those people for that. We provide assistance through ED services and optimizing geothermal loop field design, or ED at least works with the mechanical design team in that area. And through that, we see significant reduction in geothermal loop field costs for these customers that do end up adopting geothermal systems. We see significant reductions in those costs as opposed to what they would probably see if their design team just based a design on rule of thumb practices. And Ed will get into a little bit of that on how we specifically, as we say, cut the thumbs off in that process. We offer specialized training in geothermal loop field design principles, usually every couple of years. We offer it's been online training most recently. And then Ed's team has a GeoFees tool used for the preliminary evaluation of geothermal heating and cooling. And we provide our customers, account reps, and design teams free access to that tool. The results we've seen at Ottertail through bringing this process to our customers include, as I mentioned earlier, significantly lower cost of geothermal installations by working through this iterative process that Ed will talk about, as opposed to if they just relied on simple rule of thumb engineering principles. Those cost reductions we've seen have been along the lines of 30 to 40%, and that's much more significant than even our $1,200 per ton rebate that we offer through our efficiency programs can provide. And specifically, we've seen in working with some school systems, simple paybacks as low as 7 years by working through this process and installing geothermal. We've seen improved engagement from the architects and engineers that are representing and working for our customers. And even to the point of design teams working through this process with us and with Ed, and then moving on to other projects, even outside of our service territory, and recommending geothermal and assisting customers in walking through that process. And then finally, I think last but certainly not least, is systems that work. The systems that have customers installing systems that have gone through this process, we're seeing just minimal complaints, if any at all, on how the systems work, as opposed to a system that's improperly designed and never working right. Oftentimes, that architect will never even consider mentioning geothermal to a customer in the future. So that's been a big benefit. The direction we intend to take this program will include continued training sessions for the building design community in certified loop field design, as well as continued engagement with that community through the IBD Plus program. And a couple of things we're working with Ed on right now include loop field monitoring Installations of these systems involve a pretty significant investment on behalf of these customers and building owners, as well as from us at Otter Tail in bringing them through this program and then providing rebates to help offset the costs of geothermal. So for a relatively modest cost, we feel we can add some monitoring equipment and really keep an eye on how those loop fields are monitoring to assure that the system continues to work well into the future for these building owners. And another big one for us most recently that we've been evaluating is district geothermal opportunities. And we feel that in certain installations for specifically college and university campuses that there's an opportunity here to partner with them, and district geothermal or ownership of that loop field asset by Otter Tail, it really provides these customers with another opportunity to finance these installations and upgrades and makes it much more feasible for them. And for us at Otter Tail, you could see from those earlier slides on the very rural customer base that we serve, there's just not a lot of natural organic economic growth taking place in our territory. So anytime we can grow our business by growing rate base and making investments like this, it's just one more opportunity for us to continue to grow as a small utility. So I just talked a little bit about, again, just some background on Otter Tail Power, the type of customers we serve and our efficiency programs, how they operate, what our goals are, and gave you an introduction into how this Integrated Building Design Plus program works. And I can turn it over to Ed now and let him talk in a little more detail on specifically what he does and how he gets involved in this process.
Thanks, John. Yeah, what I'll do is go over how the design assistance program works with Otter Tail Power. So one of the big questions that I've always had in when a client comes to, where do you start when somebody wants a geothermal system? So basically, there's a fundamental difference between designing an HVAC system for a conventional system and designing a system for a ground source system. With a conventional system, you're typically connected up to an infinite energy source, connected to a gas line, for example, or connected to a way of getting rid of excess heat from the building when you're cooling. Basically dump it to the atmosphere and it blows away with the wind. And you're using a bit of water from the utility to help get rid of it. So basically, fossil fuels, electricity are supplied by utilities that make the investment and own and operate and supply the delivery and infrastructure. Somebody else is operating the system. You as a building owner don't have to worry about how the energy is going to get there. As a designer, somebody else is looking after the design of the system. They're building the infrastructure, building the dams, or whatever, the generating stations to deliver the energy to your place. You don't have to worry about that. Fluid coolers, you select off a manufacturer's website, or air-cooled chillers, same thing, and you base it on the peak design loads of the building. Ground source system is fundamentally different. What happens with a ground source system, you're basically working with a storage system. And when you're taking heat from the ground to heat the building, you're cooling off the ground. When you're heating the ground. When you're taking heat out of the building, when you're cooling the building, you're warming up the ground. So it can get too warm, it can get too cold if that ground heat exchanger isn't big enough. And then the system suffers with inefficient operation of the heat pumps. And in some cases, I've seen systems like that fail where the ground temperature typically just gets too warm for the system to operate efficiently. You can't select a ground heat exchanger from a website or a supplier's catalog. You've got to actually design the system, and to do that, you really need to understand the energy loads and rules of thumb. Yeah, tempting to use them, but really they can really lead you astray. So basically, when you're using some rules of thumb that are commonly used to determine the capacity of a heat pump system, 400 square feet per ton is a fairly commonly held number. 24,000 square foot building, you need divide that by 400 square feet per ton, you need about 60 tons of capacity. Ground heat exchanger, 200 feet per ton, and that's going to vary a bit from one region to another, but that's a fairly commonly used number, at least in the Minnesota and North Dakota area. But to really demonstrate how using only peak loads to estimate the size of a ground heat exchanger, if we take 3 buildings, could be a church, for example, retail store, and an apartment building. If assuming that the peak loads, heating and cooling loads are identical, roughly 40 tons, and cooling 480,000 BTUs per hour, and heating loads are about 385,000 BTUs per hour. If we design the system based on the ground heat exchanger, based on that, we're basically only designing on the peak loads. We're ignoring one of the fundamental things that an energy storage system needs to be aware of. Church, for example, is going to be cooled for a few hours a week. Retail store is going to be cooled for a lot more hours. So it's going to be dumping a lot more energy. Even though the peak load is the same, it's going to be running a lot more hours in cooling than a church would be. Apartment building, probably somewhere in between. Same thing with the heating loads. Church, because you don't have the internal gains from people and lights and things like that much of the week, the heating loads are going to be higher than they would be in a retail store or in an apartment building. But that really doesn't really show you how much energy we're actually transferring to and from the ground. You have to consider compressor energy. We're adding energy, the compressor energy used to power the compressors is added to the heat that you're taking from the building. And the compressor energy actually contributes some of the heat to the building. So that further unbalances the system that is cooling dominant. And it helps balance the system that is somewhat heating dominant. So if we use rules of thumb on the, let's say one of these buildings at 40 tons, 40 tons capacity, 8,000, it would suggest that you need about 8,000 feet of drilling. And you're trying to maintain temperatures somewhere around 32 to 35 degrees Fahrenheit on the heating side, and about 85 to 95 when you're cooling the building. Otherwise, the heat pumps start operating less and less efficiently. So one of the buildings is going to get too cold, the church, because you've got less cooling load, less heat rejected to the ground. That has the danger of getting below those temperatures. And the retail store, because you're cooling a lot more, is going to tend to get a bit too warm. It's going to get well above 90, 95 degrees. So if we're looking at the long-term operation of a system like this, they're going to operate differently, even though the buildings have exactly the same peak heating and cooling loads and are built across the street from each other. The church, because we're extracting more heat from the ground than we're putting back in, it's going to start getting too cold after about 5 or 10 years. The retail store, on the other hand, is going to start getting above the temperature that we want to see them to operate at. If the loads are fairly balanced, then we're going to see a system that is going to be stable and going to be operating continuously for the life of the building. And really increasing the size of the ground heat exchanger really doesn't help. It delays the inevitable drop in temperature in the church. Even if the system is larger than the 8,000 feet that the rules of thumb would suggest, it's still going to get drop in temperature over time. Retail store, exactly the opposite. Even if we make the ground heat exchanger 69% bigger than the rules of thumb, you're still going to get there after about 20 years. The apartment building, because the amount of energy that you're trying to shove into the ground versus how much you're taking out, you can actually reduce the size of the ground heat exchanger from 8,000 feet to 7,000 feet, reducing the cost of the system, and it's going to operate for the life of the building within that temperature range. Again, you've got to take into consideration that the software that's available these days, regardless of which software there is, doesn't take into consideration things like groundwater flow across the borehole field, which can take away excess heat, mitigate the increase in or decrease in temperature over time. It doesn't take into account the rainfall and snowmelt infiltration into the ground, or the vaporization of moisture that might be in the ground in some conditions, or the freezing of the moisture in the soil around the boreholes. That's going to help stabilize the temperatures at just around the freezing point. So the software doesn't really tell you the full story. None of the software that's out there right now can take that into consideration. So that has to be a bit of a judgment call. If you're drilling, for example, in a place that's primarily shale, even if there's moisture in the ground, moisture doesn't move very well through clay and shale. So you're not going to get the impact of water flow across the borehole field or infiltration very much. And then in that kind of a situation, the software might predict the temperatures more accurately than it would if you were in a sand and gravel aquifer where there is a lot of groundwater movement or infiltration. So the rules of thumb, really, they're going to, even based on, if you build this system based on the rules of thumb, you have the danger of the ground heat exchanger for the church getting too cold, or the ground heat exchanger for the retail store getting too hot. The apartment building, because the amount of energy you're putting into the ground and pulling from the ground is going to be fairly similar over the year, it's going to be, you can actually reduce the size of the ground heat exchanger compared to the rules of thumb. So basically, as John suggested, really, it's you're doing your customers or your clients a disservice if you're using rules of thumb to estimate what the size of the ground heat exchanger can be and what it's going to cost. So balancing the energy loads, one of the things that we've done with the design assistance program with Ottertail is to really work with the full design team, the architects, the mechanical designers, and the building owners and the contractors that are building the systems, to try and, as much as we can, balance the amount of energy that building is going to reject to the ground versus how much it's going to take out. So the design methodology really has to be somewhat different than it would be for a conventional HVAC system. An example is a library building that was a large addition was added to this building about 5 or 6 years ago, about a 24,000 square foot library in Fergus Falls, Minnesota. Rules of thumb would suggest 24,000 square foot building divided by 400 square feet per ton, 60 tons of capacity is about what you'd need. With 60 tons of equipment, 200 feet of drilling per ton, rules of thumb would suggest you need about 12,000 feet of borehole. So if we look at what the initial loads, that the way the building was proposed, what the initial loads were for that building, we've got the peak cooling load of about 56 tons, 667,000 BTUs per hour. Cooling or heating load is what, 507,000. The important thing here are these two numbers right here. 428,000 kBTUs annually that we're trying to reject to the ground versus extracting about 178,000. So that ratio is about 2.4 to 1. A lot more cooling, a lot more heat rejected to the ground annually than is being extracted from the ground, the way the original building was designed. Note that there's a 15-degree temperature setback on the operation of the building was built into the energy model of the building. So that really has an influence on what the peak loads are. So that number is actually fairly close to the rules of thumb, 400 square feet per ton. If we simply by eliminating the nighttime temperature setback in heating and cooling, that reduces the peak loads by about 6% in cooling and about 11% in heating. It increases the annual cooling load slightly, about 3%, and the annual heating load by about 8%. It's reduced this ratio from 2.4 to 2.3 to 1. So this has been a little bit reduced. This has increased a bit. And the next iteration of the energy model, basically taking advantage of outdoor air to cool a building, an outdoor air economizer. What that does is reduce the amount of energy that we're going to have to reject to the ground, 414,000 kBTUs annually. And it doesn't change the peak very much, but it does change the amount of energy that we're rejecting to the ground. You can see on the difference on here, there's a slightly larger cooling load annually than there is heating load. Running a third iteration, providing using occupancy sensors to provide ventilation or to provide lighting when it's needed. So meeting rooms that aren't occupied, we can shut the lights off, reduce the internal gains on the building, and providing fresh air based on CO2 sensors, providing fresh air only when it's needed. We've reduced the cooling load, by reducing the lighting load, reduced the cooling load by reducing ventilation loads. So now we've reduced this energy balance from 1 down to about 1.7 to 1. So we've the annual cooling energy load increased a little bit. The annual heating load increased a bit, by quite a bit more. The heating load increased simply because we're not getting the internal gains from the lights and less ventilation there. The final model that was resulted when all the changes were built into the building and some changes that were asked for by the owners, that changed the loads quite a bit. They implemented many of the recommendations that the previous energy models had shown, but that really helped improve the energy balance. So now we're looking at 380,000 kBTUs annually that we're rejecting to the ground or taking from the building. And we need to supply just under 400,000 kBTUs per hour. So it's just under a 1-to-1 ratio. So what does that do to the size of the boreholes that are needed? So if we take a look at what the rules of thumb would suggest, 12,000 feet of borehole based on the 400 square feet per ton and 200 feet of drilling per ton, 12,000 feet of borehole is what would be suggested. And if that was told to the client, the cost of drilling 12,000 feet might be more than their budget could withstand. So looking at how to start with the system, where do we go from here? First of all, we've got to have some idea, in addition to the energy loads that we're trying to deal with, we've got to try and figure out what the geology is, what that can handle. So looking at, Minnesota has a very good water well database. We can look at, here's where the library was, about 850 feet away from the library. There was a well that was drilled to a depth of about 257 feet. We got the stratigraphy. We could estimate what the thermal conductivity was. Basically, we based the initial size of the ground heat exchanger based on a thermal conductivity of 1.29 BTUs per hour per foot per degree Fahrenheit, about the average of what you would see based on the stratigraphy that we found in that water well. Thermal diffusivity worked out to roughly an average of about 0.8 square feet per day. So the initial modeling was based on what we could find without drilling a test borehole, or with spending $5,000 or $10,000 or $15,000 drilling a test borehole and running a thermal conductivity test. So try and avoid that expense right up front by getting a really good estimate as good as we could, either by looking at water well databases or by talking to drilling contractors or whatever. Next, we have to look at how much land area do we have to play with. So based on 25-foot spacing, we could accommodate up to 64 boreholes on this site. So we know how much land area we've got. Once we know how much total borehole length we need and what the thermal properties are of the soil, we can design and model the ground heat exchanger. Next thing we did was talk to some of the drilling contractors in the region. What's the depth that you would prefer to go to in that region? Are you going to run into problems if you drill beyond 200 feet, or are you going to start running into problems if you go to 400 feet? The consensus was, after talking to a couple of drillers in the area, was that about 250 to 300 feet was probably about the most cost-effective depth to drill at. So in that case, if we've got the land space available, we wouldn't design a ground heat exchanger to go to 400 feet because the drilling contractors are going to have to charge more for that. So based on the thermal properties, based on the land area, and based on the most cost-effective drilling depth, we try and design the ground heat exchanger based on within those parameters. So looking at, based on the rules of thumb, the proposed building would require about 10,000 feet of drilling. So we reduced the amount of drilling that's needed, even using the first energy model, by about 2,000 feet. So that's a fair chunk of change that helps make these things a bit more cost effective. Next step, we looked at what happens if we add an outdoor air economizer or eliminate the night setback on the system. The night setback was actually surprising how much difference that made. Occupancy and CO2 sensors are roughly the same, a slight increase in the size of the ground heat exchanger, amount of drilling that's needed. And then the final building design came in right around just over 8,000 feet of drilling. And based on what the owner requires, based on input from architects, engineers, and the ground heat exchanger designer. These were all based on 15-foot spacing initially. So what happens if we increase the spacing between the boreholes, bumped it up from 15 to 20 feet? So in the buildings that were still a bit unbalanced, increasing the spacing reduced the total amount of drilling that was needed invariably on each one of them. Once the final building design, it actually increased the length of the borehole a little bit. Increases spacing to 25 feet. And again, you see a further reduction in the building energy models that are unbalanced. So in a project where you don't have an opportunity to balance the loads, or you simply can't get there, increasing the spacing can have a fairly big impact on how much total drilling is needed. So in this case, the building that was originally proposed required just over 10,000 feet of drilling. This one is about 8,500. So that's a fairly significant difference simply by increasing the spacing between the boreholes. If the loads are fairly balanced, there's less of a difference. You don't see that. So the other thing that can be done is really look at the borehole design. The original ones up to here were looked at, the only parameters that were changed in here was the spacing between the boreholes, and we modeled it with standard grout initially, so about a 0.4 grout, and really nothing special on it. Once we started looking at the borehole configuration, the borehole layout, and the borehole design, that we're able to reduce the size of the boreholes even further. We're down to about 7,300 feet of drilling. And it really didn't make a whole lot of difference between 15, 20, and 25 foot spacing if the loads are fairly balanced. And that's how you can sometimes take advantage of a small land area, do whatever you can to try and balance the loads as much as possible. That allows you to reduce the spacing between the boreholes, the less land area. And in some cases that may make a difference. In this project, it didn't make much difference because there was land area available. But in some cases, we've run into the situation where there simply isn't the land area. You need to do whatever you can. But at the end of the day, we were able to, compared to the typical rules of thumb, reduce the amount of drilling by about 40%. Looking at the long-term performance of it, and here we've looked at with standard grout over a 10-year period, we're looking at about a 13-degree temperature increase. And that's assuming that there's no mitigating impact from water flow across the borehole field or infiltration of water through sand and gravel geological conditions. And looking at, but the building is obviously cooling dominant. So in some situations, you may get this kind of increase. In other situations, it might not be this drastic. But until you start running the system for a while and really know what the impact is of groundwater flow and things like that, it's difficult to model that. So increasing the conductivity of the grout from 0.42 and getting enhanced grout into the system, that we're able to reduce the number of boreholes from 36 boreholes down to 32 boreholes and knock off about 1,000 feet of drilling. So looking at the detailed borehole design, looking at the borehole configuration and those kinds of things can help further reduce the size of the borehole field and the cost of the borehole field. Looking at what happens if once we start modifying the building loads, in this case by using outdoor air to cool the building, we're down to 24 boreholes, 6,900 feet of borehole if we use thermally enhanced grout. If we eliminate the night setback, and this is where working with the building operator when they run the building, there's a lot of a fairly large perception, and people, some of the controls manufacturers have really promoted the use of night setback to reduce energy consumption. And in reality, it doesn't help reduce energy consumption very much, but it does make a difference on how much heating and cooling capacity you need to supply to that building. For example, if you're going to start up the building and from a 10 or 15 degree night setback, first thing in the morning, you're going to need a lot of capacity, extra capacity to run for a couple of hours to start warming up the building, and the mass of the building, all the furniture and everything else in the building has to be warmed up. So it takes a lot of energy to do that. So even with reducing the number of boreholes, we're looking at 6,200 feet of borehole from the initial rule of thumb, which suggested 12,000 feet of drilling. We're only going to get about a 6 degree temperature rise, and basically by looking at some changes to the building and how it's being operated. Looking at controlling the lighting and the ventilation on demand, we're looking at, again, very similar total amount of boreholes, 24 boreholes, 6,200 feet of drilling, slight increase here to just under 6,500 feet. But we're getting a bit better balance on the system. We're looking at a maximum of 85 degrees after about 10 years, but with only about a 5 degree rise over time. Final building design improved the energy balance further. Now we're looking at about a 3 degree temperature rise compared to the original, looking at about a 13 degree temperature rise from the original. And then once we've done that kind of modeling, then we really need to assure ourselves that the assumptions that were made on the thermal conductivity based on a review of the geology and interviewing drilling contractors or geologists in the area to make sure that that applies on the site that we're looking at. So looking at running thermal conductivity test, drilling a test borehole. By this time, we'll have had confirmation from the building owner yet that they do want to go ahead with the geothermal system. So now they're prepared to spend the money on running a thermal conductivity test. We've already done the modeling of the building, talked to drilling contractors what's the most appropriate depth to drill to, and then we can design the test borehole. We also know roughly how many boreholes we're going to require and what the total water flow through the ground heat exchange is going to be, and that's going to help determine the size of the pipe, whether you want to use 1 inch pipe or 1.25 pipe or 3/4 inch pipe, based on the number of boreholes that you have space for and the most cost-effective drilling depth. So looking at, we can design the borehole, we can locate the borehole where it is going to be, can easily be integrated with the final borehole design, and it's going to be designed in such a way that it can fit in with the right pipe size and everything else. So basically, to really describe the methodology, if you've got a client that wants a geothermal system, so first things that our approach has been is to really understand how much energy we have to deal with. What is the building design? How much energy does it need for heating? How much energy does it need for cooling? And then looking at work with the architect and to help balance the loads as much as we can from an architectural perspective. Then we do the same thing with the mechanical system, work with whoever is designing the mechanical system itself and go through that same process. What happens if you use an energy recovery ventilation system of a certain efficiency, or what happens if how are you going to control the ventilation with CO2 monitors or whatever else? Anything you can do to balance the loads is going to reduce the size and the cost of the ground heat exchanger. And then we have to deal with the site. So we need to know what the geology is. What piece of dirt that we have to work with, what can it deal with? And what kind of ground heat exchanger, what configuration of ground heat exchanger would fit on that property? In this case, the land area available wasn't good. The only really good option, there were only a couple of good options. Vertical ground heat exchanger. We didn't have room for a horizontal. There was no surface water available. There was not enough of an aquifer to really take advantage of. There were piles were not there, and a standing column wasn't appropriate on that site. So looking at the site characteristics, the geology, and doing whatever we can with the land area that we've got available to try and work out which type of ground heat exchanger is going to work best for that project. And once we've done all of those things, we know what the energy loads are because we've modeled the building. We know how many BTUs per hour for every hour of the year we need for heating and for cooling. That can be translated into energy cost based on the local utility rates, the efficiency of the equipment that's going to be selected. And we can also translate that into the size of the ground heat exchanger and the type of ground heat exchanger. And then we can get a budget cost for here's what it's going to cost to build the ground heat exchanger. And those are the two numbers that a building owner really almost invariably is going to look at. What's it going to cost? What's it going to save? And is there a decent return on the investment? If you're showing somebody a 20 or 30 year simple payback, it probably ain't going to happen. So getting that kind of information, really with a ground source system, it does take more effort on the designer's part to really answer the question, is it feasible to put a ground source system on this particular project? And using rules of thumb really isn't going to answer that. The building energy loads can change a lot based on how that building is designed, both from an architectural perspective and how the mechanical system is designed. Those things are going to change the energy loads. And I've only touched on a few of the things that can be done to a building or a mechanical system that will change the loads. But those are some of the important ones. And it's worth taking the time and the effort to go through those things and go through this exercise. And then if you can't get there with the first iteration of the energy model, if the ground heat exchanger is still too big, we'll go back to the architect, go back to the mechanical designer, look at what can be done to improve the energy balance. Look at the mechanical system again. That's where the iterative modeling comes in, and in an effort to try and balance the loads. And then if all else fails, if you can't balance the loads within the mechanical system design or the building design, and there are certain places you simply can't do that, then you might want to look at a hybrid option, might be a fluid cooler or some other way of getting rid of excess heat, or adding a fossil fuel boiler or some other kind of boiler, electric boiler or whatever, to provide excess heat when it's needed. And there's a number of different strategies that can be used to dump excess heat into the ground. In my own home, I've started a couple of years ago, adding solar thermal and dumping that heat into the ground all summer. Where I'm at, we get wintertime temperatures of about -35, -40 most winters. So looking at ways to divert excess heat away from the ground heat exchanger or reduce heat extraction or somehow balance the energy loads, that's when I started looking at hybrid options. That is after everything else that we've looked at can't get there. And then finally, once we're at the point where we've got a fairly good energy balance on the building and everybody has agreed to the building final design, and we know exactly how much property we have to deal with, then we can design and drill a test borehole and run a thermal conductivity test. So the impact that this has had on with Otter Tail's geothermal program, and we've had is kind of a unique opportunity because we've had the opportunity to work directly with the building owners, and in most of these projects, we've been involved in about a number of these projects, about 15 projects over the last number of years. Probably 2 of them would have gone ahead with a geothermal system. So about 120 tons would have gone ahead without any intervention in that. With the design intervention, design assistance program that's been provided by Otter Tail, many of these systems, about 8 additional systems, were switched from a conventional system, switched over to a ground source system. So we're looking at an additional 760 tons, about 8 times the number of projects, or 4 times the number of projects that would have gone ahead with a geothermal system that were switched from conventional to a ground source system. And what's been even more interesting is the fact that the same engineers that we've had the opportunity to work with on some of these buildings already are starting to recommend to their clients outside of Otter Tail area that they should consider a geothermal system. So these 3 that I know of have converted to the engineering firms that we've had the opportunity to provide the design assistance to have recommended to their clients, you should look at a ground source system. So in addition to the increased number of ground source systems within Otter Tail territory, there has been some spillover to some of the surrounding areas. So looking at this graphically, compared to the rules of thumb, here's what would have happened. Looking at these are the ones that were switched from conventional to ground source. So going back and forth, there's a pretty big increase. And then adding the additional ones outside of Otter Tail territory has made that pie even bigger. So, so anyways, if this is the kind of program that seems to has been working fairly successfully for Otter Tail, they've been looking at the systems that their customers have installed, and the systems that they have installed are working fairly well. So we've got time for some questions if anybody has any. Courtney, were there any questions that came through?
Yeah, absolutely. So one of the topics that's being discussed a bit in the chat is how you increased bore length by spreading the bores further apart. Do you want to touch on that briefly?
Yeah, in some cases, yeah, from I don't know the math behind it in detail, but from what I've seen in projects is that because the ground heat exchanger acts as an energy storage medium more than an energy source, I believe it has some kind of some of the impact comes from dumping the heat into the ground, and where it's dissipated into the ground, you can actually take advantage of the heat that you're dumping into the ground in the summertime and pull it out more easily if the boreholes are spaced more closely together. I don't know the math behind it that well, so I can't speak to that part of it, but that's what I've seen. I've seen that happen on a number of projects.
Sure. So someone has a question about load balancing. Is it possible, for example, in an extreme situation to have a heating only or a cooling only system?
Where I've seen that work, we actually did a feasibility study for a project in Kerala province of India. Ground temperature is about 83, 84 degrees. And when we did the energy modeling for that building, the winter design temperature was about 70 degrees Fahrenheit. And the dialog box came up in the energy modeling software. Are you certain that this energy model, the weather data that you have imported, is accurate? So yeah, the ground temperature is really high. A couple of things that we looked at to balance the loads on there is the building happened to be adjacent to a canal, and it also happened to be above reasonably good aquifer, not enough to do all of the heating and cooling. It was a large system, but it would allow us to use the 80, 85 degree groundwater to help cool off the ground heat exchanger during the off-peak times. And also, we're able to look at heat pumps that are capable of producing 140, 145 degree water, using that dump the heat into the ground. So we've got to basically increase or move the temperature range that the heat pumps were capable of. Most off-the-shelf heat pumps using our 410A, for example, you don't want to run them at much higher than about 100, 105 degrees Fahrenheit is about the top end. They start getting pretty inefficient. But with 134 refrigerant, some of the heat pumps are capable of running at 140, 150 degrees reasonably efficiently. So using that, just raising the temperature range that we're working with, and taking advantage of the aquifer underneath it, that would have made the project feasible.
Great. So does final building design that incorporates all of the load balancing measures that you had put in place in the examples?
Mm-hmm.
Oh, perfect.
Yeah.
Okay. And then often someone asks the question that they are brought in to do a feasibility study very early on, before any energy loads are calculated. How or what have you used as a tool to convince them to continue looking at it and go into full energy modeling to keep looking at geothermal?
One thing that we've done in the past is to use existing energy models of existing buildings that are similar to the building that our client is looking at. So for example, if they got an apartment building in Albany, New York, for example, and we've done a similar building in Toronto, we would take that same original energy model that we did on the building in Toronto, might make some modifications to the size and to the window to wall ratio and things like that on the energy model, and do that fairly quickly without spending a lot of time on it, and run that energy model using Albany weather data and see what happens, and then do a review of the geology of that area and look at the land area. And we can do that fairly quickly by possibly talking to a few drilling contractors or looking at water well databases or whatever. And in about a day or two, we can get a fairly reasonably solid number on that. It's not going to be exact. It's going to be probably 15, 20, 25% off of where we end up, but it's going to be a lot more accurate than rules of thumb would maybe suggest. At least you've looked at what the geology is and got a reasonably good estimate of that type of building in that climate. The other thing that we've done as well is, and that's kind of the whole point, that we worked with Otter to develop the GeoPhase website. It's got a whole large library of energy models and different energy efficiency measures that can be considered. Energy recovery ventilation system, adding the domestic hot water loads, for example, on some of the buildings, or looking at changing the type of glass that's in the building. The glass can have a fairly large impact on the cooling loads and as well as on the heating loads. And looking at that, looking at a archetypical building for that area, and looking at running a ground heat exchanger calculation based on those energy loads on that building, and looking at the different energy efficiency measures that you could do, that can get you an answer in probably about half an hour.
Great. So I just want to ask if the data shown in the presentation, they look like they were based on monthly loads. Were the simulations run as monthly or hourly simulations?
The initial simulations that we typically run, simply because of the speed of the calculations, and depending on the software that you're using to model it, we'll typically use monthly loads because they can run more efficiently. But once we're getting to the final design of the building, we'll want to confirm that with the hourly loads of the building. And the reason for that is because most of the software out there, whether it's GleePro or whether it's Earth Energy Designer or whatever, or GLD, there's an assumption made for the duration of the peak loads. How many hours in a row are you going to have a peak cooling load or close to peak cooling load? And if you're in something like a place with a lot of computers running all day long, that peak load might extend from about 8 or 9 in the morning to about 4 or 5 in the afternoon. In other situations, depending on the occupancy of the building, that peak load duration may only be an hour or two. So that's the big thing that varies then in running it with monthly or hourly loads. But when we're doing the final design, we'll run the hourly loads just to confirm what we found using the monthly loads, simply because it's quicker to model it using monthly loads.
Great. Do you know if ground loop softwares model the hydrological or hydrogeological activity? If so, do you know how to incorporate that in the model if they don't already include that?
Certainly the models that use the G function calculations, and that includes Earth Energy Designer, GleePro, and part of GLD, they take into consideration only conduction of heat through the ground. If there's groundwater flow across the borehole field, it doesn't model that, or infiltration of rainwater or anything like that, it doesn't model it. The software that uses the peak loads, you can make an adjustment on some of the software that will take into consideration that yes, there is groundwater flow, or no, there isn't. It really doesn't quantify that. In order to model that accurately, you'd really want to get a water well test in the area, and basically it's really to try and determine how much groundwater flow there could be across the borehole field, what the depth of the fracture zone is. For example, in a limestone aquifer, is the fracture zone maybe 10 feet deep, or is it 100 feet? And that would have an influence. If you're near the ocean, you might have some influence from tides going in and out and things like that. But there's no easy software that I know of where you could inexpensively model that. There is There are hydrogeologists that use something like FeeFlow that will do that, but it's a pretty expensive process.
Great. So we have one more question. Are bore fields always square or rectangular in shape? And would alternative layouts use larger space in the center zone or smaller spacing at perimeters possibly reduce the size of loop fields?
That's a really good question and very appropriate question because and it depends to some extent on what the energy balance is. If the energy balance is fairly even amount of heat you're dumping in and taking out, then a square or rectangle close to a square field, it operates very similarly to a borehole field that might be 2 boreholes wide by 20 boreholes long. If the loads are unbalanced, that's one way you can use to help mitigate that. You're touching more dirt, unaffected dirt, that with more of the boreholes, if you've got a long skinny borehole field, than if you've got a square or close to square borehole field. And that makes a big difference. You're basically touching more dirt, unaffected dirt with a different layout. And that's something that you can model very easily in some of the software. So it's certainly worth looking at.
Great. So if we missed any questions today, we will definitely forward those on to you, Ed, or you, John. And I want to thank you both for presenting here today. And anyone that's on the call, look forward to events coming up in the future as we take some deeper dives into commercial design. Thank you everyone for attending, and we will get this up on our YouTube channel soon. Thank you again, Ed. Thank you, John.
Thanks, guys.
Thank you.